In this set of notes, we're going to look at GLM estimation and model fitting. And what we're going to do in this set of notes is we're going to look at a lot of the theory that goes in behind this. Later on in the course, we're going to focus more on the applications and specific types of GLMs. So previously, we introduced the framework of GLM and we discussed the basic properties of the score and the special connection between the score and the natural parameter that exists in exponential families. And in particular, remember, we're going to be working with that exponential dispersion family, and we're going to be working with that specific format or notation that we had. And so just like we talked about last time, how we're going to have that natural parameter, we're going to have that b of theta, those are going to appear here as well. So recall from Module 3 that it's often the case and always the case in regression modeling that f of x depends on multiple parameters. And we know this because we typically have, we've got the intercept parameter, we've got the slope parameter in simple linear regression, and then we know in multiple linear regression we're going to have many coefficients. So all the preceding results can extend to the case where we're interested in a vector of parameters. So before, I pretty much wrote everything as just a single parameter, but really we can do all of this for a vector of parameters. So think instead of just having theta, we've got theta 1 through theta p. And so we can now extend our definition of the score. And so the score is still going to be a function of theta, but now instead of looking at a single derivative, we're now going to have a vector that we take the derivative of. And so that's why you see the gradient notation here, because remember, essentially when you have the gradient notation, that just means you're going to take the derivative of the vector. And so here we've got the gradient of the log likelihood, and this is what the elements of u are going to be. So if the first element of theta is theta 1, notice that the first element of u is going to be the log likelihood of theta, and we're going to look at the derivative with respect to theta 1. So now the score is a p by 1 vector, and to denote this, I'll often write the score vector as u. So a little bit just note on notation here. Here I've chosen to denote u with a capital U because u is random. We could look at, the expected value of u. But u is a vector, and so a lot of other sources that you're going to look at, since u is a vector, we'll use a lowercase u. Because remember, when we talk about vectors and matrices, typically vectors are denoted using lowercase and matrices are denoted using uppercase. We are going to be working with some matrices here. So just, that's just a note on notation there. As long as you define what you're working with, it doesn't really matter. So the MLE is now found by setting each of those components of the score vector equal to 0. It's basically the exact same thing we did before. And we could look at the distribution of u, and it ends up that u still has expected value 0, and we could show that u is approximately normal with mean 0 and variance v. And then even further with exponential families, here u is going to be equal to the sum from I equals 1 to n xi. So this would be, in terms of x, if we had multiples in our sample, minus b prime at theta, a phi in the denominator. So pretty much the exact same thing that you had before. And recall that in thinking about maximum likelihood estimations in terms of the score, we see that the MLE is found by setting the sum of the observed scores equal to 0. And we saw this when we first defined the score function back in Module 3. And, we talked about how we could look at the distribution of the score, and then we could see how from that we could use that to get the distribution of the MLE. And so we know the approximate distribution of u, but the problem here now that we're working with GLMs is the distribution of theta hat is going to be more complex because that function b prime of theta may be complicated and nonlinear. So before, when we first looked at the score function, I kind of showed you all an easy example where you could start with the score function and very easily see how to get the distribution of the MLE. But now, because of how theta is embedded in that score function, it's not going to be as straightforward now. So we could then go on and talk about the sampling distribution of the MLEs. And so we know the sampling distribution of a maximum likelihood estimator is approximately normal. And so this relationship provides another perspective on information. As the information in the sample goes up, the variability is going to go down. And it also allows us to use familiar results about the normal distribution to construct test and confidence intervals for the individual parameter theta. Furthermore, it tells us how the MLEs for various parameters are correlated, allowing us to easily work out sampling distributions for linear combinations of parameters. So here I've got kind of another way, if you want to think about it this way, you could also be doing a quadratic approximation of the log likelihood. Noting that the log likelihood, the normal distributed, is actually quadratic, it should come as no surprise that theta hat is also normally distributed. So with all of that being said, the preceding derivations have all assumed we have identically and independently distributed observations. This, of course, is not the case in modeling the natural parameter for theta I. For each observation is different, we expect it to change depending on that explanatory variable. And indeed, understanding how the explanatory variable affects the outcome is kind of the entire point when we do these types of analyses. So, of course, we don't go about estimating theta I directly. It would be unstable. So instead, we impose a relationship with theta and the explanatory variables, and that's really governed by that systematic component of the GLM. Now, we spent some time talking about the canonical link, and we saw that when we work with the canonical link, we have some really nice properties. So we're going to continue assuming that we are going to work with the canonical link. And so what we're doing here is we're going to be directly modeling the natural parameter. So remember that when we talk about theta as the natural parameter, theta can be a function of the parameters dealing with that distribution, or from the distribution. So we saw that, for example, with the Poisson distribution. The natural parameter was a function of the mean of the Poisson distribution. And so you can still work out relationships and distributions for other links, but the expressions are a little bit messier. So it ends up, if we look here, we know that for the canonical link, we've got the natural parameter is equal to x transpose beta. And so if we take the derivative of theta with respect to beta, notice that just becomes x transpose on the right-hand side. And so what this does is, if you were to actually go through and do all the derivation, if you have this, it's greatly simplified. And so it ends up that if we're going to estimate beta using maximum likelihood, we can apply the earlier results, and we end up with exactly what we would expect. It ends up that beta hat is approximately normal with mean beta, and then the variance is given by V. But the only catch here is we have to work out that information with respect to B, or beta rather. So if we're working with a canonical link, we get this really nice formula here. So we have phi in there, and then we have x transpose wx. Now x is an n by n diagonal matrix with entries are determined by the second derivative of beta for theta I. And so remember, when we worked with the Poisson distribution in the last note set, we saw what that was equal to. And so since W is a diagonal matrix, remember that diagonal matrices are going to have zeros on all the off diagonals. And then here what we're saying the diagonal elements are equal to would be the second derivative evaluated at theta I. So if we were working with a Poisson distribution, all of these would be the same, like the functional form would be, but then we would just evaluate them at theta I. All right, and then that brings us to the sampling distribution of the betas. So the sampling distribution of the regression coefficients of a GLM with canonical link. So again, approximately normal with mean beta. And then notice here we've substituted in what that variance is, or the information. And so from here, we can go through and find confidence intervals and hypothesis tests just like we typically would. We know that if we take beta hat minus beta divided by the standard error, that's going to be approximately distributed as a standard normal. And then here we would have the formula for the standard error. Notice this looks very similar to what you saw before when you looked at linear regression. Now, we do have to make some assumptions here. We're going to assume there's a reasonable way to estimate phi. And then the matrix W is going to be evaluated at beta hat. All right. So now that's kind of some of the theoretical properties of beta hat, but the regression coefficients of a GLM, we have this more practical question, which is how do you actually solve for beta hat? You know, that's fine. We see these theoretical distributions, but how do you actually solve for that estimate? And it ends up that that's a much more challenging question than it might initially sound. When we worked with linear regression, we had this really nice closed form for beta hat when we would go to solve it. You might remember we even saw in R. We could work directly with the matrices and we would get those estimates. But when we work with GLM, it's not as straightforward. There are no closed form solutions. So what we can do is you can kind of combine some ideas from a Taylor series approximation and iteratively weighted least squares to obtain an algorithm. And so we're going to look at 3 different methods here that could be used to estimate beta hat. Just for your information, you don't necessarily need it here for what we've done because we've kind of taken this high look at everything. But if you do want a review of a Taylor series approximation, I have included that at the end of the notes. So the first one here you actually very briefly saw in 675, and that was the Newton-Raphson algorithm. So just as a reminder, the Newton-Raphson method iteratively solves nonlinear equations. And it's useful when finding the maximum of a function. Well, we know that we've been doing maximum likelihood estimation, so that sounds like that could be a really good fit here. And so the idea is you start with an initial guess of the solution, and then you find a second guess by approximating the function in the neighborhood of the first guess by a second-degree polynomial. And then you find the maximum, and then you repeat this until you have convergence. And so more formally for a single parameter, and this space is just extra space, suppose that you've got your initial guess. What you do is you find the horizontal intercept of the tangent line to the curve, where we look at the first derivative of the log likelihood, and then that is going to lead you up to the next guess. You make a substitution and you repeat. And so here we would like to apply this algorithm to find the value of beta hat, which maximizes the log likelihood. And we can do that by starting with that score vector. So here I formally have written out the score vector. Notice here I've written it with the transpose. The reason for this is we typically, when we write vectors, we write them as column vectors. We saw that during the discussion in class. So in order just to write this in a horizontal format, that's why we've got the transpose there. So here, we're going to let M, HM, and beta hat M, they're going to denote the U vector, the Hessian matrix, and the estimate at the iteration M, where UM, HM are evaluated at beta hat M. And so just to remember here that the Hessian matrix, what that is the derivative of U. And so the Hessian matrix is going to be a P by T matrix of all of those possible second derivatives. This is different than the matrix W, because remember W is a diagonal matrix that has, those second derivatives on it. The Hessian matrix is the full matrix of the derivatives. And it ends up that the Newton-Raphson algorithm can calculate the updates using this piece right here, where U is the score vector, H is the Hessian matrix, and both of which are evaluated at beta hat M. And then this continues until those changes are sufficiently small. So this is really similar to what you saw in 675 when we applied the Newton-Raphson algorithm for MLEs. We could also do what's called the Fischer Scoring method. This is just another alternative iterative method. It just uses the Hessian matrix in a different way. So what the Fischer scoring does is it uses what we call the expected information. So recall we saw before there's this connection between the Hessian and the information. So in other words, the information is the negative Hessian we would expect to observe. In practice, it's usually easier to deal with the Hessian we actually did observe. And so that's where you come to what's called the expected information. And so we end up, if we define J to be the expected Hessian, you end up with something very similar to what we had up here with Newton-Raphson, except now we work with the expected Hessian instead. Now, typically you're going to see no difference between these two methods because if you use a canonical link function, these are going to be exactly the same. Now the last one is the iterative least squares algorithm. And so previously we saw weighted least squares estimation, and it ends up there's a relationship between the Fischer scoring and the weighted least squares. So as we've discussed previously, we can obtain MLEs by setting the score vector equal to 0, and it can be shown for a GLM using the canonical link that the score vector can be written as follows. So in the above equation, mu is a function of x beta. However, it doesn't need to be a linear function, and if it's not, we'd like a closed form solution for beta. So we can apply a Taylor series approximation to obtain the following approximation at point beta tilde. And then we have this proposition, if G is the canonical link, we end up with this piece right here. Okay, so now with all that being said, what we really care about is this next main result, and it ends up that we obtain the following linear approximation to the score for beta. Okay, and so this approximation is based at beta tilde, or equivalently mu tilde, which are treated as constants in the above expression, thereby rendering the score equation linear in beta after the approximation. And again, recall this approximation will be accurate near the fitted values of mu tilde, but not necessarily accurate far away from them. So what we end up with, and here's the really important part here, is for these iterative least squares, here is the estimate that you end up with for beta hat. And notice this looks very similar to what you had for least squares. And what's happening here is W plays the role of the weights in weighted least squares that you saw previously, and for that reason is often referred to as the weight matrix. And what you will actually see in the homework for this section, if you work with linear regression, okay, it ends up that W is just the diagonal matrix of all ones. And so because of that, if you were to substitute this in here, and then for Z up here, you actually just end up with pretty much the same estimates that we had before. So for the canonical link, W is going to be entirely determined by that mean variance relationship, and it plays a prominent role in the variability of beta hat as well. And so here we require that superscript M because it's the case of unknown weights, where W and Z will change depending on beta hat and vice versa. And so as we saw earlier, one way to address this problem is to iterate the process of reweight estimate until convergence. And so just like when we saw the iteratively weighted least squares algorithm before, we have pretty much the exact same thing here. And so those are just kind of three different methods. You're never going to do these by hand. Really, you just want to have that overall general idea of what's happening, because we are going to perform these in software when we look at specific types of GLM. So just kind of as a note here, recall that for linear regression, that full rank design matrix implies that there is exactly one unique solution to beta hat, which minimizes the residual sum of squares. A similar result is going to hold here. If X is not full rank, then there's no unique solution that maximizes the likelihood. However, there are two additional issues that could arise. Although a unique solution exists, there's no guarantee the algorithm is going to find it. And it's possible for the unique solution to be infinite. And in that case, the estimates are not particularly useful and inference kind of breaks down. Now that first issue that we've got here, that one is pretty uncommon. If it exists, usually we can find it. And so the last part here in the notes, if you're interested, I do have a review here of Taylor series expansions.